Hi everybody. Uh, my name's Doug Lyon, and I'm here to give you a little overview about design patterns. If you have any questions, you can shoot me an email at lion@docjava.com, or you could visit my webpage at www.docjava.com. Some of you may know some Java, and some may not. I'm going to operate under the assumption that you might know a little bit about object-oriented programming and object-oriented design. And I'm going to introduce for you the notion of design patterns. Then I'm going to introduce the notion of our first design pattern called the strategy pattern. And then what we'll do is a series of examples with real code. And if you have any questions, just interrupt or shoot me an email. Happy enough to see if we can't address the issues surrounding the details of the code. So first question, what is a design pattern? And the answer to that is, well, it's a solution to a well-understood and recurring problem. Generally speaking, in object-oriented design, you might find a way to implement some design patterns in procedural languages, but it's generally speaking not easy, and the design patterns came about because of object-oriented programming. One thing I notice about all design patterns is they have names. The names give us formalized designs. If you are interested in, for example, bridges, there are design patterns for bridges. For example, a suspension bridge has a fairly well understood design. A trestle bridge has another relatively well understood design. So when we talk about these different types of bridges, we think about the formalized designs surrounding those bridges and ways in which the bridges are characterized. Similarly, if you're an antenna designer and someone says, I want a Yagi antenna, you think, well, Yagi antennas, they've got a director, a reflector, and a radiator. And if somebody says, well, I would rather have a dipole antenna, well, dipole antennas in general have a tap and then a couple of leads going to either side of the tap. So when we think about designs, we think about the names of the designs and how they're formalized and characterized. Design patterns can be reused. Design patterns are what I call an outcome of software engineering maturation. In the past, we didn't have design patterns. I took software engineering courses years ago. No design patterns there. And then if we think about why design patterns are important, well, it's because they change the way we think. And perhaps that's the most compelling reason to study design patterns of all. If you have these new names, we have, I think, what we would call jargon or nomenclature. And every mature discipline has its own jargon. And this well-understood vocabulary of communication enables us to be efficient when we communicate with others on our team. So that in and of itself, not only does it change the way we talk about how we do our programming, it also changes the way in which we think about our programming. And another, I think, compelling argument for the use of design patterns is it enables the reuse of object-oriented designs. And this is critical because software engineering in the past has relied upon large software libraries in order to obtain reuse. But now we can have reuse of designs, and that's something that we didn't used to see before design patterns. And so now, without further ado, I thought I would just introduce for you the basic concept of the strategy pattern. The strategy pattern, as we pointed out before, it has a name, strategy. It's a design pattern, generally speaking, implemented only with object-oriented programming languages, and it centers around the basic notion that you're not really sure how you want to solve the problem, but there are certain characteristics about the problem that are common for all solutions. So we want to be able to address a class of problems. And so if we are trying to address this entire class of problems, then we would like to use our context for trying to select from different implementations of solutions to those problems. And so reusing subroutines and reusing functions, well, that may be something that we have seen in the past, but if we have a way to reuse a design that provides us with an implementation to a specific class of problems, it allows us to create a toolkit. And that toolkit, which relates to that class of problems, will essentially enable us to do software reuse. In one way I think about Eli Whitney going in front of Congress and taking apart a whole bunch of guns and then putting them back together and they all function. It was the beginning of interchangeable parts, the dawn of the Industrial Revolution. It enabled the subcontracting of individual parts, and it enabled mass production. This was all because the parts were made according to a specification. In the world of component software development, we would like to be able to develop components that can be treated as though they are interchangeable parts. And in some sense, the strategy pattern helps us do that. And it does it because it uses an interface. Now the interface is going to give us I'll call it a software specification enforced by the compiler. Interfaces in Java in general only contain implementation of static final constants. They do not have implementation of method bodies, no behavioral implementation. As a result, the interface is almost a pure specification. And when you comply with that specification in the implementation of classes which implement the interface, then you have met the spec, and now your class can be plugged into a framework that uses component software development. My principle, this is the simplest principle, I'll call it, make the interface as simple as possible. And this is one of those things where people might say, well, this is one person's opinion, and that's true, but I can tell you that from experience, if you have a complicated interface, it's very difficult to maintain it. And the reason why is because interfaces are not flexible. Once an interface is created, it creates a standard. So for example, if I have an AC outlet and that's my interface, it's very hard to change that standard. If you want to go from a 3-prong interface to a 2-prong, you need an adapter, and that's another design pattern. But if you want to just stick with 120 volts and 60 cycles, well, that becomes a standard that's very difficult to change. Now, if you're in some countries where there's 220 volts and 50 cycles, you're generally speaking not going to be able to plug in without some sort of transformer or some sort of adapter. So since not all interfaces serve all applications, you have to be very careful about how you curate the interface. And if you said to me, well, all cars are pretty much the same and I can drive any car, they all have the same interface, it's a steering wheel, it's a brake, it's gas, that's it. I can drive a sports car, I can drive a station wagon, it's all the same. But a plane is really different and it has a different interface. And maybe I know how to drive a car, but I certainly need to study in order to learn how to fly a plane because it has a completely different interface. Yes, there are pedals on the floor, but they don't do what you think. So here's a basic interface called runnable. And anything which implements the runnable interface, well, it will have a run method. Now the question is, how much weight is there in a simple interface like runnable? And in my project, which I'm working on now, I have 286 classes which implement the runnable interface. I'm also working on an image processing program, and the image processing program has an image processor interface. It's the simplest possible interface I could come up with. It's what I would call a garbage in, garbage out interface. Let's see if we can make this in blue. And the goal is the input image goes and gets changed in some way by the process. And after it's changed, a new image is created, or the original image is altered, and then a return image is the new image, the processed image. And you look at it and you go, well, an image processing program, image goes in, image comes out, sounds good. You want to change this to make it so that you can deal with floating point images instead of fixed point images? Well, now all of a sudden you have to change 104 different classes. That's really hard. That's going to take more than a couple of weekends. So as a result, if you decided that, well, 24-bit images are just not good enough for me, I need something better. I need medical images with, 64-bit DICOMED image inputs from MRIs. This is not going to work for you unless you do some kind of a conversion. Sometimes those conversions can be lossy. So as a result, once you make a decision about what an image is, that is a decision you kind of have to live with for the life of the program. Program to an interface. Well, turns out if you go back and take a look at the image processor interface, if you told 10 people to write operators that did 10 different things, but they all programmed to the image processor interface, you can take that element, those operators, and put them into your framework and extend your graphic user interface to give your image processing program a little bit more richness. One interface, you can have many implementations. In fact, the number of different operators is unbound. But you've got to live with that interface after you've designed it, which is why I always say, make the interface as simple as possible, but no simpler. The interface maximizes cohesion because all of the operators implement the same interface, but since the operators don't know about one another, it minimizes coupling. One of the basic metrics of object-oriented complexity is inter-object associations. If you have a whole bunch of objects that know about a whole bunch of other objects, then you can change one object and break the other objects. So this becomes a problem. Minimizing coupling minimizes fragility in the system. But if you change the interface, everything breaks. And so in some sense, the interface becomes, I will call it, a source of fragility, but also a source of stability. If the interface does not change, then everything should continue to work, even if you change the graphic user interface in a major way. Even if you go from a desktop computer to a mobile device, all of the operators should continue to work. So here's the basic idea. The client uses whatever context they may arrive at in order to select the strategy for the algorithm which implements an interface. What we see here, I don't know if you're familiar with the UML, so we'll just take a little bit of time to explain it. This is composition. And what it says is the context has access to the interface and allows the interface to select from any one of a number of different algorithms. And these classes which implement the algorithms are concrete classes. That is to say, they're non-abstract in the Java parlance, which means you can make an instance of them. So this is very good for operators. It's great for selecting multiple algorithms. It's great for creating a framework, like an image processing framework, where you have a whole bunch of related operators. And it's implementing, using the interface, polymorphism. It enables us to do what I would call component software development. It gives us the interchangeable parts of a software engineering system. But I think more importantly, you have to be very careful about how you curate your interface. The interface will enable teams to work together, so the interface had better be a good one. And of course, it promotes code reuse. What you need to do to create the interface is identify the behavior, which is common to all of the elements in some related tasks, such as image processing. And keep in mind, an interface provides a specification. Do not make the spec very complicated. Use the simplest possible interface you can. In Java, we typically have what I would call the dead end of subclassing. Nobody else calls it that, but I do, because Java does not have multiple inheritance. So if you have a class which subclasses a parent class, that's the only parent it can subclass. So it can't inherit behaviors from multiple superclasses like you can in C++. In fact, Objective-C also suffers from this limitation. However, you can implement as many interfaces as you like. So if there's something in the spec that you want to add, you can just create a new interface and then start implementing that. So it's very good in terms of the strategy pattern. The strategy pattern is very good for classes that differ in behavior and differ in their details but have a common specification that you want to code to. It gives you the ability to do what I call runtime selection of the implementation based on a context. So the concrete strategy, that's the implementation of the specification, is going to be equal to a function of that context. So here is an example where we have a robot which has some strategy selection capability to change its behavior. And it will move. Robots move. Let's see if we can get the pen going here. Right, all the robots move. And so the interface that they have a ability to move, and the question is, how shall they move? Well, they can move in an aggressive way, or a defensive way, or a normal way. And you can change how they move, and all we know about the robots is that they move. And at this point now, I think it's time for demos. So let's do a little demonstration and see what we can do to try and make the strategy pattern come alive.